Go. Okay. Get started, and great pleasure to introduce to speaker Giorgio Giannone. He's been a long-time collaborator with us back when this group was at MIT IBM. In fact, he's been around with us during the late night hours. We've sort of pulled in, working on this whole language model customization, even back when it was even called InstructLab. So we've been working together for a long while, and after a couple of stints at like Microsoft, Amazon, now he's back with the AI innovation team as a research scientist. Giorgio's expertise is in modeling, probabilistic modeling, and diffusion models. Today's talk, he's going to focus on his work with aligning VLMs, visual language models, and specifically on like sampling-based vision production. So without any further ado, I will let Giorgio start today's talk.
Thank you, Shiv, for the introduction. And yeah, today we're going to discuss about visual language models, and in particular, how to align different modalities. Visual language models can be seen as a generalization of language models, and in particular, as language models that can also process visual information. And where conceptually this is like a simple change, in practice, we introduce a lot of complexity because these two modalities, vision and language, are represented in very different ways inside these models. And the topic today will be, the focus today will be in particular on how to align small visual language models. And for small, we mean models that are in the range of 1 billion up to 7-10 billions. And before we start, let's try to understand why aligning visual language model is hard. So in these last few months, there has been a lot of work done for language modeling. And in particular, there is a lot of interest in this ArcGI challenge. And ArcGI is basically like a benchmark to try to understand how far analogical reasoning in language models can go. And there has been a lot of progress in scaling computing, scaling inference, thinking models. Yesterday, OpenAI just presented a new agentic version of ChatGPT. And all these kind of like improvements are mostly language model based. And in particular, they all rely on somehow the intuition that we can scale compute and we can scale search. And together, scaling compute and search is letting us improve these models without necessarily like modifying the model themselves. We can explore the sample space. We can let the model like self-play, try different ideas, try different make errors and correct from these errors. So this new phase where basically like self-play in the real environment is happening for language modeling has been called the age of experience or the era of experience. And the core idea is that we started with like an era simulation where we had to build very specialized environments. For example, like for AlphaGo, AlphaZero, we had to build a Go environment with a specialized reward. For AlphaZero, we had to build like a different kind of environment, but we had to kind of like simulate these environments. And then we moved to an era of human data, and this is kind of like the period that started with like the release of ChatGPT and large language modeling in 2021, 2022. And in this phase, the models were basically, we scale compute mostly. The model were basically like, we collect more data. This data could be annotated by humans, could be annotated by remote modeling. But in general, like it was in a period where like a human annotation was central. And now that we're like in a new phase, this phase of experience, where the models are good enough, general enough, that we don't need to build a simulation environment. We can let the model directly work in a real environment. For example, like in solving GitHub issues, solving chemical problems, solving mathematical proofs. And we can let the model learn directly from experience and from making mistakes, solving these mistakes, and receiving feedback. And the core intuition for this age of experience is that AI systems can improve without necessarily like retraining and without having access to their components. But we can improve them providing more compute at the inference line. And the core idea is that if you have like an input and we want to obtain like an answer, we don't need necessarily, we can kind of like ask the model to provide the answer directly, or we can kind of like, we can kind of let the model think about the answer. We can provide the model with like additional compute, and this compute can be allocated to simplify the problem, like break the problem down to different components, thinking step by step, or search for a solution. Here you can see some of the classic way this compute is allocated. In this case, for example, we use a chain of thought prompting. That is the simplest approach for inference time scaling. In this other plot, you can see majority voting. So basically, instead of having like one chain, we have multiple chains, and then we select the one that is providing us the most consistent answer. And on the right, you can see a more complex approach that is basically like what we would call like a searching approach, where we're not only like asking the model to break the problem step by step or parallelizing the problem. Now we are really like searching for a solution in the sample space. And this search can be done in many different ways. But the interesting point is that thanks to this search, performance can be improved without retraining the models. So these models are really starting to reason, and for the reason like this is one of the ways, for example, like RKGI results are being obtained, like providing the models with more computed inference time. And the first model that was really provided like evidence that inference time compute can be used, can be scaled in principle without plateauing was the O1 series from OpenAI. And on the right, we can see scaling compute, like training time. So basically like training the model, larger model, more data. And on the right, we can see scaling inference time compute. In both cases, we see like clear improvements, and we on the same benchmark. These are like mathematical questions. So scaling compute and scaling inference, so scaling data and scaling search, they're both working extremely well for these benchmarks. However, there is a limitation. Like the limitation is that typically we can scale in this way when there is a way to verify the solution of our problems. This is a general, in computer science, is a general like problem, much wider than machine learning. But in particular for language modeling, there are like problems with different complexity. And this complexity can arise because generation is hard or because verification is hard. All problems that are in this region, problems that we can easily generate today and we can easily verify. And problems that are in this region are problems that are hard to generate and easy to verify. And in general, every time there is like a verification mechanism, for example, mathematics, chemistry, tool use, coding, all this field have like a clear verification mechanism. Every time that you have a verification mechanism, we can leverage inference time compute and inference time scaling to basically improve the performance on a specific task, on a specific problem. However, if verification is hard or verification is unclear, for example, in this region, it's leveraging inference and scaling becomes much harder. So reasoning is unclear how we can guide or how we can provide feedback to the models when verification is challenging. And in this case, when we say verification is challenging, what we mean with a challenging verification is not necessarily like hard computationally. It can also be hard or unclear. For example, here you can see creative writing. What is the right feedback for creative writing? There are many different ways to express the same idea or the same concept. Or let's say that you want to verify security of a piece of software. What's the right way to provide feedback for that piece of software? So there are many fields where verification is hard it's unclear, or it's difficult to define. And these are kind of like all problems where, like, for the moment, inference time scaling hasn't been that effective. However, like, just to clarify that when feedback is available, progress has been extremely fast. And here you can see a sample from like recent papers where leveraging inference time scaling, smaller models, open source model, for example, like DeepSeek, or smaller models, just the QM25 with 7 billion parameters. These models are able to reach, leveraging like more compute at inference time, the performance of, like, for example, an O1 level model. So when feedback is available and verification is available, performance can be improved. However, when verification is not available, what can we do? And this is what this is the core point we're going to discuss today. We want to understand how we can reason or how we can improve performance when verification is not readily available. And in particular, we're going to focus on a specific subset of reasoning, that is visual reasoning. The reason we care about visual reasoning is because, as we mentioned before, we have interest in visual language models. And visual reasoning is particularly challenging because we don't only need the model, we don't only need like the model to be able to leverage like inference time scaling, and we don't only need like verification mechanisms. We also need to align the visual modality and the language modality. So for this talk, we will define a visual reasoning. And the most important part of visual reasoning will be the capacity for the model to interpret visual information, make inference. Of course, there are many ways to define visual reasoning. The idea of visual reasoning started with like David Marr and the stereo computation for the visual systems in human. However, we will assume here like a simplified interpretation. And for us, visual reasoning is the capacity to interpret visual information to make inference. And let's make this a little more clear. In particular, let's define what a visual language model is, because we just like discussed about the model, but we didn't really introduce how to build a visual language model. A visual language model is a generalized language model. The main difference is that a language model typically takes an input text. Instead, in this case, we also have image information in input. And in terms of like architectures, it's very similar to standard transformer, where together with language tokens, we also input the visual tokens. And these visual tokens need to be harmonized with the language tokens. And there are many challenges that arise. For example, like the model can hallucinate information that is not in the visual input. The model can forget objects that are in the visual input. For example, there can be recall issues. And again, as we mentioned multiple times, in general, there will be like misalignments between visual and language. Let's see an example of what this exactly means. What do we want from the visual language models when we try to do reasoning? On the left, we have an image as input. And this image is like a very simple image. This is a table. It could be a studio with a laptop. And now we ask our model, we instruct our model to describe this scene. The model will provide us with a description of the scene, and there will be like some issue. There are like some issue with the scene. In particular, as we can notice for the red part of this text, the model is kind of making mistakes about the position or the geometry of the scene. For example, here you can see that on the right side of the desk, there is a laptop open and ready for use. The laptop is on the desk, but it's not on the right side of the table. And another error is that to the left of the desk, there is a floor lamp. And this is, of course, for us, it's extremely easy to see. The lamp is on top of the table, so this cannot be a floor lamp. This is a table lamp. And this is a case, for example, like that we could call a hallucination case. The model is hallucinating objects that are not there, or is not understanding the relation between the table and the lamp in this case. And then underneath the desk, there is a black wire basket, which is likely used for cable management. And of course, it's true that there is a basket, but it's not underneath the table. And this is not, of course, for cable management. So these are all mistakes about the scene. But the biggest mistake here is that the model is completely forgetting about the chair. So you can notice that we have like the chair is the main one of the main components in this image. It's extremely easy to visualize for us. It's like it's easy to see this one chair, which is 4 legs, and somehow the model is unable to like recall the chair. So with just this simple sample providing this image, we have hallucination issues. The model is describing things that are not in the image. We have recall issues. The model is forgetting to provide description for objects that are in the image. And this is the core problem that we're trying to solve. We want to solve like issues of recall and hallucination, improving alignments between vision and language. And again, just to reiterate why this is a challenging problem, because when you try to integrate the vision and language, the representation for vision and language are a different level of abstractions. For example, vision typically we analyze pixel by pixel. Language is much more like high level, at the concept level, symbolic in a way. There is a representation gap. There is a misalignment between the modalities, and there is unclear verification. So it's unclear how we can provide verification, for example, for a situation like this. What is the right visual reasoning in this case? How can we verify that? How can we verify that, for example, like this caption is correct, or it's kind of like analyzing correctly the image provided as input? And the core idea of this work is to leverage grounding models, a feedback mechanism. Of course, this feedback is not a verification feedback. We cannot fully verify the problem. However, our hope is that we can provide enough feedback to still steer the model and elicit better alignments between vision and language. So what is a grounding model? A grounding model is very similar to a classic detection model, where we input an image, we have a fixed set of classes, and we output bounding boxes with labels. The difference between a detection model and a grounding model is that in a grounding models, there is no fixed set of labels, but we can provide like an adaptive, labels can be adapted. This means that we can provide, in principle, any text to the model. The model will be able to like merge this text information with the visual information. And the output of the grounding models will be a set of bounding boxes that provide us some information, some approximate information about the geometry of the scene. For example, here in this case, the set of these grounding models, the output of these grounding models would be a set of bounding boxes that are going to tell us something about the structure of the scene. And we're now going to use these grounding models to provide feedback to the model that we've seen before. And using this feedback, we hope to improve performance, or at least to improve alignments between vision and language. And this is the core of this work, and in particular, this mechanism, these alignments through grounding the feedback between the vision and language is what we call sampling-based visual projection. The alignment is performed in 3 main phases. The first phase is an inner loop sampling. So we sample the model, and then we leverage grounding to improve this sampling. We then use the grounded model and the base model for scoring. So there is no external feedback directly, or we don't need to train an external reward model. We try to leverage the feedback provided by grounding as a reward model. And finally, there is an adaptation loop that we use to kind of like we use to kind of amortize the new information in the model itself. Let's see an example of how it works. Let's go back to the image that you've seen before. This is exactly the same slides that I showed you before. We take an image and we sample a base model, and the model will make a few mistakes. And these mistakes will be related to position, objects that are not there, or objects that are missing. So forgetting objects. Now we take the information that we obtain in output from the model, and we ground this information in the image. We take the grounding model. In particular, for this work, we select a grounding dyno. It's quite popular model in the grounding community. So we take these captions and we take the image information and we ground this caption in the image. What we have now, we have a bunch of like bounding boxes that provide us approximate information about the geometry of the scene. We then convert these bounding boxes in textual format, and we provide this bounding box information as additional context for the model. Now, together with this additional context, we ask the same questions, and we prompt the model again, and the model will provide us new captions. And this new caption now is informed by the context. And this is, for example, like what you can obtain when you sample the model again. And now notice that there are like a few changes. For example, like thanks to this additional context, the model has a better way to understand the structure of the image. And for example, before we saw before that there was a mistake about the position of the laptop. However, this mistake is corrected in this new caption. Now you can see that on the desk there is a laptop with a black screen and silver body positioned toward the center And so we fix, for example, like a positional issue. And notice that this time the model is able to detect that there is a white chair in the office, a white office chair. And this time, instead of describing a floor lamp, the model is describing a desk lamp. And to the right of the desk, there is a black white basket. So the model is no more thinking that the basket is like below the table, but it's kind of like towards the right. So this is an example of like providing better context. Now the model is able to kind of better ground the output text in the visual information. And this is like basically what we call grounded sampling or sampling-based visual projection. We then repeat this process n times, and we leverage the a weighted log ratio between the logits of the grounded model and the same and the logits of the ungrounded or base model. And the idea here is that basically, like leveraging this ratio, we are able to understand where the grounding model is providing novelty or diversity. And because we make an underlying assumption that the grounding model is helping us to better ground information, textual information in the visual input, ideally, high scoring samples will provide us information to improve the model. So we repeat this n times. We use the log ratio between the logits of the two models, and then we use the scores that you obtain to rank and select the top K. And typically we sample 20 times, and the top K will be the top 10%. So we select two captions for each image in most cases. Finally, we have an adaptation phase. In this adaptation phase, we consider the selected captions, the images, and we train the model without providing the context. This means that during the adaptation, we modify the weights of the model using the gradient-based adaptation, but the model doesn't have access to the bounding boxes. So the model does not have access to the grounding information, but has access to the improved captions. And why we do this? We do this because at test time, we want to obtain a model that can be used just running a forward pass without necessarily relying on grounding models at test time. We just want to inject this additional information in the model itself.
There is a question on YouTube. Sasha just sent.
Where can I see that? Yes, but where can I see the questions?
Read it out.
I can just read it out.
Yeah.
How can you handle images that are intended to confuse people?
It's a very good question. So we will see later on that we have some benchmarks that are called like the adversarial benchmarks that are exactly trying to achieve this goal. They're trying to confuse us. They're providing like mistakes that are obviously confusing, and we'll see that the model helps in that situation. In general, like what we're trying to achieve here is to provide enough feedback for the model to elicit the model to elicit better alignments in the model. This is not self-improvement. This is mostly like elicitations of capacity that the model already has, but because of misalignments, for example, not enough training or not enough data in a certain regions, somehow the model doesn't understand exactly how to use the capacity. Here we are trying to elicit the capacity, leveraging approximate feedback. And we'll we will see like in one of the benchmarks that is called POC, we will have like adversarial questions and adversarial tasks that are exactly trying to misguide the model or also misguide humans. Are there other questions?
I know that's it.
Okay. Okay, we perform a sampling, scoring, adaptation, and then and we apply these methods to the lava family, and we apply this method to models that are like 0.5 billion parameters, 0.5 billion parameters, 7 billion, and 13 billion parameters. We use 1,000 input images from the Coco dataset, and we use these 1,000 input images for like prompting the model, obtaining samples, performing grounding, and so on. And now we will see evaluation for captioning, referring task, object recall, and hallucination reduction, and then image to text and text to image consistency. So captioning means that simply we're trying to see if the model is better captioned after adaptation, after applying SVP. We're trying to understand if the model now is a better captioning model. And the blue we test on 3 different datasets: NoCaps, Coco 2017, Flickr 30K. They have different. These datasets have like different complexity, different images, and different structures, different resolutions. And we can see that in all these cases, the base models is the blue. The base model is the blue bar, like what is lava, and the orange and the green bars are like 2 variants of our method. We can see in all these cases where when we apply SVP to a 7 billion model, in all these cases we're like a large improvement in captioning capacities. This is kind of like corroborating our hypothesis that using like this feedback is helping the model to better ground the language in the visual input. And of course, if the model can better ground visual and language, the model should also be able to become a better captioner. So captioning is a downstream task if you think of alignments as a foundational task for a visual language model. We apply the same experiment for the 13 billion model, and we also see like large improvements. But let's see exactly what does it mean that the model is improving for captioning. What is the difference? So here again, I provide an image, and this is like a yellow bus, and then I ask the model to describe this image. And there are a few mistakes. This is the base model without our adaptation mechanism. There are a few mistakes. For example, like the model thinks that this is like a double pass. It's not true. But then there is a mistake that is a subtle mistake. And the model is also a car parked on the left side. Now, it's probably difficult. I don't know if you can see, but the model is discussing this component of the image. And you can see that this is not a car. This is like the front part of bus. It's quite hard to see, and we can understand why the model gets confused. However, if now we apply our adaptation mechanism and we ask the same question to the model, what happens is that now the model is able to understand that there is a bus there. The model has a better like overall capacity to ground the visual information in the language caption. And you can see that the model now is telling us that in the background, another bus can be seen, albeit much smaller and less prominent. So this is like the numbers that we've seen before, the improvements in capturing capacities. This is the improvement. Now the model is able to better understand the scene, to better understand that there is a second bus, and provide us with the correct information. And even like in a way, telling us that the bus is smaller and less prominent. In a way, this is like not easy to say.
Where is the next bus?
Yeah, it's here.
Either. Like a little bit like darker yellow on the top.
There is no, it's not yellow. It's
Yeah, it's up the top left.
top left.
Yeah, top left.
That's very hard to see.
yeah, it's hard. It's hard for us. It's hard also for models. It's hard also for models. Okay, and then this is what we can do with capturing. Then we try to explore a referring task. What is a referring task? A referring task in these situations is captioning for a specific region. So, for example, like we ask the model to describe only a portion of an image. For example, like we ask the model only to describe something that is inside the square. We'll see a few examples like in a minute. But again, these are the same plots. You can see this is referring using a bounding box as anchor for the regions that we want to describe. You can see large improvements on 3 different data sets. We can use segmentation mask to describe these regions and to delimit the regions. And also in this case, we see large improvement. What do we mean? What is this improvement in practice? So this is what we provide to the model in this case, an image, and then we provide like a marker on top of the image. And we ask the model to only describe what is inside this marker. This is a hard task because the model has not only to understand, has not only to align a regional language, now the model has also to understand that we only care about one portion of the image. So the model has to somehow interpret the marker. In this case, the marker will be the bounding box or the square, understand that we only want a description for that region. So if we take visual language models without our method, the model is not able to kind of like understand what we want, not able to interpret the marker, and is not able to kind of like describe what's inside there. The model starts describing like the full images with some mistakes, but in general, like this is not what we want. If now we ask the same questions to the model after adaptation, we can see that the model is concise because now the model has only to focus on a specific region and is telling us what is inside that region. A man wearing a white hat and sunglasses. This is not perfect. For example, we would like to know more about this, to know more about this man. So what this man is doing, what he's wearing, like the t-shirt, what he's doing with his hands. So it's not like a perfect result, but it's much closer to just describing that region. Here we can see another example. This is like, again, we ask it to describe only what is in a certain region. We only want to know what is inside this square. And of course, this is very easy for us. This is like a slice of pizza. However, if we ask this question to the model, without using our method, the model will just tell us that the pizza is in a box. So basically, the model is kind of like describing the full. The model is kind of describing the full image. If now we ask the same questions using this like adaptation approach, the model is able to interpret the marker and tell us what we have inside the marker. Again, this is not perfect. It's also a function of how good the grounding feedback is, but it's in the direction that is providing. It's telling us that a better alignment is helping us to obtain a model that is better at referring things, better at captioning. Okay. And now we're going to evaluate like the capacity of the model to record objects and to reduce hallucination. And this is the answer to the question that was asked before. How do we evaluate the model when, for example, someone is trying to deceive the model or the images are trying to deceive the model? Is benchmarking the input for the model is an image, and then a description of this image. Then we ask questions to the model, and these questions can be organized in 3 different buckets. One buckets are like random. We ask about random objects. We don't ask about objects that are in the image. We ask about random objects. For example, we ask if there is a bottle in the image. Then there is a popular setting. So instead of asking like random objects, we ask about objects that are like very common and typically present in the image. Finally, there is an adversarial setting where we ask something that looks like some of the elements in the image, but is not present. For example, in an adversarial setting, it could be there is a peer in the image. And in this particular case, there is an apple. At least I think it's an apple. And that, again, there can be confusion because there are like objects or components of the images that can look similar, but they are different names. They are different. They are different things. This is like what we call adversarial. We try to kind of like push the model to make a mistake. Very easy here for the model if there is no understanding of what the image is representing. It's very easy for the model to make a mistake. this image in the visual input. And again, we can see a few metrics, and typically we see F1 score, accuracy, and we compare with like the base model, few models with like adaptation mechanism that are similar to ours. Also, like we compare with a model that is using direct preference optimization, DPO, with collected data, sample data. And in general, also in this case, we can see that our approach is quite effective in reducing hallucination and improving object recall. And the green line is our best model. And another interesting thing that we studied is try to understand the empirical distributions of the number of objects that are mentioned in the captions. And in particular, we measure, we take a sample of captions, and we count the number of objects that are mentioned when we apply grounding, and the number of objects that are mentioned without grounding. And what is interesting is that typically when we ground the image, the model will tend to mention less objects. This is, if you think about the referring task, for example, when we want only to know something about a portion of the image, this makes sense. We don't want the model to describe everything that is in the image. We want the model to only describe a portion of this image. So this is an interesting ablation, and that is also telling us something on how these models improve or how these models align vision and language. It's not just linguistic alignments, it's also a practical. In practice, there are also components that can be measured, for example, in terms of like a number of objects generated, or number of objects that are grounded in the image. And then we also compare our method with like test time adaptation mechanism, train time adaptation mechanism. So here, test time adaptation means that we don't fine tune the model. We just try to use more compute at test time. This is what you would call inference time scaling for a language model. Then train time adaptation, these are mechanisms that use more compute at inference time, and also adaptation mechanism similar to the one that we're using. And also among these models and in this benchmark, we can see that we perform quite well, and we are like close to state of the art. Regarding the question that was asked before, adversarial is this column. It's providing you the adversarial scores. And obviously, when we have an adversarial question, performance will be lower. But well, it's important to understand what is the gap between like the adversarial score and the average score. And you can notice that for these models, for the model that we train, the gap is relatively small and is still performing quite well compared to the baselines. Okay, and we measure like metrics related to captioning, referring, hallucination reductions, and object recall. And in all these situations, we saw like results that are telling us that better alignments between visual and language as a foundation for visual language models is helping us for a large amount, a diverse type of task, downstream task. Here, now we are trying to understand if a better captions can also be a better input to generate new images. And in particular here, what we're going to do is that we take a real image, and on the left, this is a real image. Now we ask a base model and the model adapted with our mechanism to caption this image. Then we use these captions for a generic text-to-image model. Text-to-image models are models where you input text and they generate images. For example, like stable diffusion, flux models, Midjourney models, all these models, DALL-E, all these models are like text-to-image. You input the captions and you output the generated image. So what we want to measure here is the consistency between the input real images and the generated image. If alignments between text and images, between language and vision is improving, thanks to our method, we should be able to obtain a better consistency between the base image and the generated images. Because the text to be able to better represent the input information. And let's see this example. We have a real image as input. This lady, and there are like a few deers. It's quite like, it's not a common image. And now we use the base model to caption this image, and we use like a standard text to image model. In particular, we use the flux model, FluxDev model, to generate to regenerate the image. And now we try to measure how close they are. And you can see that when we use the base model, these images are quite far. There is some components, for example, like the umbrella, people around, but the overall content is lost. Now we apply exactly the same mechanism using our method, and you can see that even if, of course, there are differences, we have like a woman, center of the image. She has an umbrella. We have a bunch of deers around, and we have people in the background. You can see that the overall structure is much closer to our input, and this is like an indication that SVP, the sampling-based visual projections, is really helping in improving alignments between text and image. It's not like a superficial effect. It's not something that we see only through the benchmarks or through like these standardized data sets, but it's something that we can really see even in a situation like this, where we're trying to measure consistency between a real image and a generated image. And another example, again, left is a real image, quite uncommon, I would say. We caption and we use a base model to generate an image, and we can see that some parts are like some parts are like similar, and there is a lot missing. There is no tree, there is no greenery. And now, if we use our model after adaptation, again, there are differences also here, but we can see that the overall structure is much closer. The overall structure resembles much better the content of the input image. We have like a tree. The model is assuming this is a Christmas tree. It's a reasonable assumption. And we have a donut. The donut has a different, like, I would say, probably like it's of a different kind, but overall, the image structure is much closer to what we want. And finally, let's go back to our favorite image, the one that we used to basically like introduce the problem. The real image is this one. We know that if we ask the model to describe this image, there are a bunch of mistakes. For example, the model telling us there is a floor lamp, and this is the floor lamp generator. It's telling us that the laptop is on the right, and it's telling us that the basket is below the table. And as we mentioned before, the model is completely forgetting about the chair. Where is the chair? Now, if you use our model after adaptation, this is what you obtain. You obtain a floor lamp, you obtain a laptop in the middle of the table, we obtain a chair, and we obtain a basket that is towards the right of the table. Again, there are differences. This is not a perfect matching, but the consistency and the resemblance with the structure and the visual reasoning that the model is doing resemble much closer what we care about in the input image. Just some limitations, like we have seen like positive results, and of course we have seen that the method can improve alignments between language, and these alignments can help the model to better perform for many different downstream tasks. However, there are limitations. One limitation is that this method is not introducing new knowledge. So we are basically like limiting our capacity to alignments between vision and language. So we don't have the new knowledge introduced in the model. This means that, for example, if the model doesn't know something, and we ask something about the visual question answering, for example, we ask specific information about a building, or we ask specific information about a monument. For example, like we ask something about the Torre Eiffel, we ask something about this famous monument, and the model doesn't have that knowledge, our method cannot improve that. So there is no new knowledge injection, and this means that for tasks that are like knowledge intensive, for example, visual question answering, we cannot really improve performance. And the second limitation, that of course it's obvious, is that, as we mentioned, the core of this method is to improve. The core of this method is that we are trying to improve alignment between vision and language. And these alignments cannot easily be verified. So we don't have a verification mechanism like in mathematics. We only have like approximate feedback. So the capacity of our model to improve or to the capacity of our model to elicit better alignment or better modality alignment, it's limited by the quality of the grounding model. So if the grounding model is not good enough, or if the grounding model is not able to really ground the text and image, there is that is the bottleneck. We will not be able to do much in terms of like improving performance. That is like probably the biggest limitation of our method. And finally, for larger models, training with more data, with a better distribution, and many of the newer models, they also have like some grounding mechanism embedded inside. Our method probably are like limited, could be limited in terms of like improvement and efficacy. Okay, this is the core of the method, and the method has like these three components: sampling, scoring, and adaptation component. And the core idea is that we can use grounding models as feedback to improve alignments between vision and language. Thank you.
And then questions. Yeah, we can wait for like 5 minutes for questions and then conclude the talk.
I have a question. Like in terms of implementation, how is the position of like the spatial cues being provided to the visual language model? I think you have a slide for it. I just did not fully understand.
Yeah. It's so
Elaborate a little bit more. Maybe go to the slide that you kind of.
Yeah. I think you can. We have like an example also here. The way we provide this grounding information to the model, it's in language format. So we want to kind of like approximate language as much as possible, because these models, these visual language models, are really like generalized language models. So what we do, for example, in this case, we have an image. We use a base model. We sample the model. And now we use a grounding model to obtain grounding information. The grounding information are this, for example, like this, are visualized using this square that you see here, these bounding boxes around objects. Now, these bounding boxes have coordinates, and they have like corresponding labels, or corresponding like noun phrases that are like telling us what is in the box. We take these labels, we take the coordinates in a certain format, and now we use these labels and coordinates as additional context for the prompt. And now we prompt the model again. So this is like at the end, in practice, during the sampling step, the context is simply like additional text. And this additional text, hopefully, or at least this is what we aim to, is providing us a link between the vision components that the grounding model is extracting and the language component. In terms of like representation, this is like a language representation. Of course, there are limitations because we need the model to understand at least approximately what this like coordinate mean. And there are like few details on how you can represent this coordinate to make them like invariant to the solution, to make them like easier to read for the model.
Right.
And for example, like because the training distribution of these models, it's known, it's fully open source. You also know like if the model has seen some of these bounding boxes and what's the format of some of these bounding boxes, and this can help the model to kind of process this kind of information.
So it's actually the bounding box is in a coordinate format, like for something like this.
Yes. They put basically after you sample, you grab, you provide a new prompt. In this new prompt, the context, it's basically like the only new thing. It's like this context, and this context contain information. This is the format of the bounding box.
So it is effective because the base visual recognition the text model has seen this in this training.
I've seen some of this in the training.
I think this format of bounding box.
In this for this particular model. So we So not all the models. So we use one format for all models, and but not all the models have seen the same format. So, but in general, like, you need the model to like at least some minimal understanding of how these boxes are done. However, the model has not seen. Model has not. The model doesn't have a capacity to output bounding boxes in this specific case, and this is not our goal. We want to use this grounding information to improve alignment or to improve the caption. And then we only want to adapt on the improved caption. We don't want to use grounding at test time. We want to, at test time, the model, it's a normal language model, or it's a normal visual language model that you can run and you can obtain the result. All the result that we see, the numbers, are all obtained with a single forward pass without any external intervention. The grounding model is only used during adaptation on these 1,000 images that we collect.
I think it sort of answers the next question, but here's one from YouTube. Does this method work with non-rectangular bounding box regions? Example segmentation models.
I only tried during inference, during like training, during adaptation to use bounding boxes for simplicity. However, the results that we've seen for referring, for these referring results, here these results are for like when we refer to the region with a bounding box. Here is when we refer to a region with a segmentation mask. So we don't explicitly adapt using segmentation mask. However, because in the model has some understanding of what the segmentation mask is, what the bounding box is, it's able at inference time kind of leverage segmentation masks, like leverage like marker that are like organized as segmentation mask, and to describe only the region inside segmentation mask. So we don't use different markers during adaptation, but at inference time, the model is still able to kind of like understand if a region is represented with something that's not the bounding box.
So in this case, for segmentation mask, the input is not your standard coordinate matrix, right?
No, like at inference time, we input only the segmentation mask. It's only visual. It's on top of the image.
I see.
So yes, like for example, like this something like this. Instead of like a bounding box, it will have maybe a mask like this.
It's almost a full image with a mask.
Yeah, they're called like markers. Like it's a different kind of marker. The model is still able to kind of associate them. If you ask, tell me what is in this region,
Right.
the model is able to associate like the region, the limitations with the goal that you have. I think there is a question also like on Wormate.
Yeah.
What if the grounding model is a non-simple trained on the contaminated data? On the contaminated data. So grounding models are typically trained. I'm not sure what you mean here with contaminated data. Or like grounding models are typically trained with a large amount of like regions and associated labels. So the grounding models, for example, like why we use images from COCO dataset. So COCO is a dataset that has been seen by basically any model around. The grounding model has seen images from COCO, like the lava family model has been trained on images from COCO, and many datasets that are maybe not, many datasets include COCO images. Any detection models has been trained on COCO dataset. So the reason we select the 1,000 images from COCO is because we know that visual information has already been seen by all the models that we're considering. Now it's like what we know the training distributions for the visual language model that we use. One of the main reasons we select the lava instead of, for example, like more powerful model is because the training distribution for lava, the data used for like aligning the modalities, the data used for fine-tuning visual language, it's fully public and you have access to it. So you can easily understand what the visual language model has been trained on. For the grounding model, like for many of the grounding models, the training distribution is not public. So there is always like a risk of contaminations. However, in our particular case, we don't use we only provide the input image. We never provide the textual information. Everything that is language is generated by the model. This means that we don't really care if the images are present in the training set of other models, because the images that we selected from the COCO dataset, on the COCO 2014 dataset, have already been used to train our model. So we're not providing new information to the model. We're only trying to better align visual and language information to elicit basic capacity that the model already has. We're not trying to. This is not a form of self-improvement, because grounding is still like a form of external feedback. This is a form of elicitations, like computationally live elicitations to kind of fully use the capacity of the model. I don't think this is I don't think this is happening in these grounding models that I'm using. Data is not public, but the overall structure of the data is public. There's always a risk. Again, we don't have access readily to the training set. There's always a risk, but I don't think it is like we are in this kind of situation. But also, I'm not an expert about the topic.
I was actually curious about the text to image and image to text conversion. I was thinking if that could sort of be like inference and if we could use one of those image to text model verifier and basically scale the text to image with that as basically keep sampling until that generates. Like if we can somehow come up with a metric which measures the difference between.
I would say again, it depends how we define a verifier. So in what I told the verifier is something that is giving us like a almost noiseless signal. So for example, in mathematics, we can receive signal about the correctness of certain parts. Right? Here in this case, we can define a similarity metric, but the signal will have always some level of knowledge.
Like this will be some sort of like similar to how we use reward models.
Yes, exactly. It's more similar to how we use like learner reward models, how we use like some learner scoring. So I think it can be done, but up to a certain point. And I don't think that this can be done really. I think all these mechanisms are kind of like eliciting capacities, not necessarily like providing the form of self-improvement. Self-improvement means that the model is improved. We improve the model on a task, and the model is not losing all the capacities, or it's improving on other capacities. Elicitations means that we're kind of like to leverage all the capacity, the full capacity of the model. There are, for example, like when you have a language models and you do SFT of the model. In many cases, the data that we're using is a small amount, and it's only helping you to align the way you ask the question to the model to the output. It's not really a way to provide, not always a way to provide more knowledge, but it's a way to fully elicit the capacity of the model. And here we're trying to do something similar. There's an assumption that the model already can process these images. The model just need to understand how to process it. And then when this adaptation mechanism, for example, here we just use 1,000 samples. It's a very small amount of data, 2,000 because we use the top two. This data is kind of helping the model to understand, okay, when I see this kind of input information, I want this kind of output. So to be concise, I think it can be used, but up to a point. I don't think it's going to give you like results, scaling behavior similar to what we see for mathematics, where in principle more compute is going to give you better results. There is no real plateau. Where when you have like an approximate reward, you can approximate so like reward hacking, you can plateau. So it's a scaling up to a point, and then you can even like decrease the performance in some situations.
Yes, if there are any more questions, we can. Let's thank the speaker one more time and thank you everyone for joining.
Thank you so much.